All right, so hello. This is the presentation about the project Securing Data Communication with Adversarial Neural Cryptography. This is the title, and we'll be looking at how this works and what it does. Okay, so a basic overview. The idea is based on GANs, and it is an implementation of generative adversarial networks. For this, for to work on this and to understand what the presentation is, the viewer needs to understand GANs. Okay. Now, what is the concept behind adversarial neural cryptography? The idea is to secure a communication channel without human input. We know that all of our communication channels, like our messaging apps, our internet browsing, or all our uh, communications between clients and servers on the internet is encrypted with some of the other form of encryption. Okay, at least, at the very least, it will be SSL encrypted. At higher levels, it will be end-to-end encrypted, etc., etc., etc. So all of that requires that you implement a well-established algorithm, and a well-established algorithm is not always available. It is always available, but the idea behind this is to not use an algorithm, to have two parties essentially learn how to communicate a channel without without a human telling the parties how to communicate. Okay. The scope of this minor project, again, this is not the scope of the entire project, but the scope of this minor project is that first we have to establish how synchronization between two loosely connected networks will work. I'll explain what loosely connected means. Then we will apply adversarial neural cryptography to these networks and see how they perform. And and we will test the security of this network. We will see how it performs, what it's how well it encrypts. We'll measure various metrics, etc. And we'll also measure its performance against a human. Okay. Now, first of all, how do GANs work? GANs work on two concepts. First, neural networks, and second, game theory. Neural networks, we know they are systems based on probabilistic logic. They are a model of how the human brain works. Again, this is not something that I need to explain. They behave, for essentially for our purpose, they behave like a high dimensional function with a large number of parameters. Now, there are three things that we need to keep in mind when talking about a network. One, the dimensions, as in the features. Okay, the features are the dimensions of the network, and the parameters are the relationships between these features. How much a feature is related to another feature is the parameter, and that parameter is learned by the network. Okay, and the third thing is the hyperparameter. The hyperparameter is not something that is derived from the learning process, but it is something that the trainer or the programmer puts in. And hyperparameters again need to be optimized, and all that is another deal. Okay, so the idea behind GANs is based on game theory. In game theory, there is a concept of Nash equilibrium. What is Nash equilibrium? When two agents, imagine two agents are playing a game. Let's say they're playing a game of chess. Okay, if they're playing a game of chess and there are two agents, Alice and Bob. Alice has strategy A, where A strategy. What I mean by strategy is it is a function that Alice will use to determine its next move. Okay, so let's say two players are playing a game. Each of them has a function which takes in the current state of the game and outputs the next move you should make to win. Okay, that is your strategy. So Alice has strategy A and Bob has strategy B. So in in game theory, the concept of Nash equilibrium proves empirically that uh, two agents will eventually arrive at a state where none of them can make progress in the game without changing their strategy. So if you take a certain strategy and keep using it, both parties in the game will arrive at a state where you can no longer proceed further. You can no longer defeat your adversary without changing your strategy or without them changing their strategy. This is called Nash equilibrium, and uh, this concept is used in neural networks to train GANs. Okay. Now, this was a sort of preface on how GANs work. We'll look at a typical example of real and fake images. Let's say we have a generator G and a discriminator D, and these are basically functions for our purpose. And the generator G takes in some noise Z or Z. So this noise is input to the generator. Now this can be anything, right? It needn't necessarily be noise, it can be anything. And the generator generates a fake image G of Z. Okay. Now this G of Z is a fake image that is generated by the generator. Okay. Now what we do is we take a batch of these fake images. We'll generate lots of them. We generate a batch of fake images, and we remember which ones are fake. And we take a batch of real images which come from this database here. We take a batch of fake images, and we take a batch of real images, and we remember which ones are real and which ones are fake, and we mix them up together. And the mixing essentially randomizes them. Now what we do after that is we take this batch of images and we give it to the discriminator. The job of the discriminator is to give us a probability between 0 and 1 as to how likely is it that this image is real. So if the generator says 0, that means the image is fake. That means the discriminator thinks that the image is fake. And if the probability is 1, that means the generator thinks the image is real, right? So the generator's job is to determine which images are real and which images are fake. And this it does on the basis of this probability. Now we know which images are real and which are fake, and we label them accordingly. We give a label of 0 to fake images, and we give a label of 1 to real images. And now we train the discriminator. How bad this discriminator performs drives the learning of this generator. What does this mean? That if the discriminator is not able to classify fake images as fake, then the generator is doing a good job. Then the loss of the discriminator is high, and the change to the generator is low, is a small change. That which means that it is very easy for the generator to fool the discriminator. Now, if the discriminator is doing its job very well, right, if it's able to easily classify real versus fake images, then the loss will be high and the generator will be trained faster, meaning the changes inside the generator will be larger. So that means that the generator's job is not being easily done. That means it's not easily able to fool the discriminator. It needs to be trained better. This is the concept of GANs, and it's formally mathematically described by this equation here. This was first given in the Ian Goodfellow paper in 2014, right? This V is the combined loss function of this entire system, and min G and max D here, this means that the generator tries to minimize this function and the discriminator tries to maximize this function, right? And both of them arrive at an equilibrium. Here these log units mean the loss. The d of x is the output of the discriminator when the image is real. Okay, so this log of d of x, the log of a number between 0 and 1, is based on how close that number is to 0. If the number is close to 0, that means that the log's value is huge. If you look at the graph of the log of a typical log function, the value of the log close to 0 is huge in the negative direction. Now this means that if the discriminator thinks that a real image is fake by giving a probability close to 0, then this log term will be huge. Okay, that means the loss of the discriminator will be large. And at the same time, if its output is if it is unable to classify this term as fake, which means that d of g of z, now g of z was the input of a fake image. If it is not able to classify this as 1 and make this term 0, then this means that the discriminator is bad at classifying fake images. So uh, if the discriminator is bad at classifying real images, this term will be large. If the discriminator is bad at classifying fake images, this term will be large, right? E here, E in probability means the expected value. Expected value is the average or mean value of a quantity over a large range. So if we do this thousands of times, the expected value of this term, of whatever term, is given by E of that term. Okay, so this is just the mathematical representation. Okay. Now, what is ANC? ANC is adversarial cryptography. It's based on two concepts: adversarial training and cryptographic concepts. Okay. What we are doing is we are applying the concept of GANs to secure a communication channel. What does this mean? This means that we are training two networks to learn how to communicate without us telling them how to communicate, right? No human input is given, and the cryptographic communication is done without using standard functions. Okay, and this is an important point, the security of data depends on whether a third party can understand it. This is our basis for training the network. Our idea is that the network is as strong as an adversary trying to break the communication, right? If the adversary is not able to break the communication, that means that the channel is secure. And if the adversary can easily break the communication, that means the channel is not secure. That's simply what ANC is. Now we'll look at how a network model works. Let's look at two parties, Alice and Bob, and they will communicate using this scheme. Okay, there is a plaintext message P. This plaintext message P goes to Alice. Alice is a neural network, and you can look at Alice as a function. Alice outputs the ciphertext C. Now, since Alice is random at the beginning, this ciphertext C will also be random. This ciphertext goes to Bob. Bob is also a neural network, and Bob tries to decipher the original plaintext P from the ciphertext C. Now, at this point, both networks are random, so we don't know which. We don't have any guarantee that they will perform this operation of encrypting and decrypting in this fashion. We don't know that they will learn the same function in the forward and backwards directions. For that purpose, we introduce a key K that goes to both of the networks. Now, how this works is a bit of a complicated issue, but essentially what this key does, it synchronizes these two networks. Now, I talked about loosely connected networks at first. So what is a loosely connected network? Two neural networks which are communicating with each other, essentially sending their outputs to each other without sending their entire internal state, are said to be loosely connected. They can communicate even with a single bit of information, and over time it has been observed that they will converge at a common state very quickly, and this is said to synchronize the two networks, meaning that their learning processes will be exactly the same, and you can tweak this network such that they learn the exact same function in the forwards and reverse directions, right? So that is our goal. We will try to synchronize these networks such that they learn the same function in the forward and reverse directions, right? Now, the loss of Bob, meaning how bad Bob is at predicting the original plaintext from C, goes to Alice as the reconstruction error. Now, the reconstruction error will be used by Alice to either increase the level of encryption or decrease the level of encryption. If Bob is able to easily understand all the ciphertext, then Alice will produce harder and harder problems. If Bob is not able to understand even the most basic of ciphertext, then Alice will have to reduce his level of encryption. This is how Alice will work. Now, in typical GANs, what happens is that Alice will try to defeat Bob, but here Alice is not defeating Bob. Alice is working with Bob to try and establish this communication. Okay. Now, this this system works, the security of the channel depends on a third party listening in. So let's introduce a third party. Now this ciphertext will go to another neural network called Eve, and this Eve is an eavesdropper. Uh, the job of the eavesdropper is to listen in on the communication and produce its own version of the plain text PE. Uh, the loss of Eve is how bad Eve is at predicting the original plain text from the ciphertext. And this loss goes back to Alice, meaning that if Eve is bad at predicting the original message, then Alice will continue using its current encryption. And if Eve is easily able to understand all messages, then Alice will have to increase its level of encryption. Now, in this scenario, you might look at Alice and Bob and see that they are basically doing the same job. But Bob has access to this key. That is the whole idea behind this system. That without this key, a network should not be able to learn the communication between these two parties, even if it has complete access to the communication channel, right? And the key will be shared between these two communicating parties. So that is the idea. That is the whole system of work. How we will deploy this is that we will build a sender and a receiver, Alice and Bob again. They will have a message that they communicate with each other, and we will have a server in between. And we will have attackers who can clearly see all the messages on the server. We will build the server such that all intruders are easily able to see all messages. And the intruder's job will be to look at the message and try to decipher what the message was. If the attacker is clearly able to understand what the message is, then the server will inform Alice that your encryption was not good enough, and the training process continues. This is the deployment version. This is the system architecture. This is based on WebSockets, and we will, this is the implementation part. But again, that's not terribly important from the research perspective. Again, so now the attention areas. Attention areas are those things that we need to look at in greater detail. Synchronization and homeomorphism, these are two important things. Synchronization between Alice and Bob is important because without the synchronization, the system would never work. Without the symmetric key shared between them, the whole system will collapse. And if they are not able to synchronize with a key, then the whole point is defeated. And another thing with synchronism is that it is never perfect. Since a neural network is a imperfect, probabilistic system, the synchronization is never perfect. So the data loss that occurs due to imperfect synchronization has to be corrected for, meaning that you have to apply error correction codes like Hamming codes and Shannon codes, and it's all those things to try to reconstruct information that was lost. Then homeomorphism. Homeomorphism is the concept that an encrypted piece of data will look the exact same to a machine uh, as a plain text. Now, characters don't have any meaning to the machine, right? Yet they have some intrinsic information built into them. The idea of homeomorphism is to establish such a crypto function such that if you put a plain text into it, the amount of information and the orientation of information stays the same in the output. So what this does is that it enables analysis of the outputs of the encrypted text or the ciphers without compromising security or privacy on the network. So with homeomorphic encryption, you will be able to make predictions on the user's usage data, etc., without knowing exactly what they're talking about and without knowing exactly what they're doing, right? Because you can then cluster similar types uh, of conversation or similar types of messages together. That's what homeomorphism is. It essentially tells us that there should be a one-to-one relationship between every input and its encrypted version, meaning that the encryption function should be, in mathematics as we say, bijective, meaning that it should be reversible and reversible with only a single outcome, with only a single uh, input, as in that the uh, that it is to reverse the function. If you have the key, you should not be in any there should be no probability that we are 90% sure that it can be this, or 10% sure it can be the other thing. That's what homeomorphism is. So to achieve homeomorphism in this system is another goal that we need to look at. Okay, this was a question slide for people who wanted to ask questions. Okay, the schedule, this is not important. Work until now we've done is that we've taken inferences from literature review. We have looked at a few papers that say that it is possible to do this. We have looked at papers which tell us it is possible to synchronize these networks. We have looked at agents. We've looked at this experimental inference that an agent is only as strong as the environment it's put in. And now this is something that is a sort of thing that we need to understand. Although a network might be secured in this way, the communication channel is only as strong as the attacker, meaning that if the attacker is very weak, if it is never able to decipher any message, then the sender will have a false sense of security. They will never try to improve. So that is a problem we need to solve, that the agent is only as strong as the environment. That's another thing that comes from game theory, also in reinforcement learning, etc. So yeah, another thing is that although a neural network might not be able to decipher the message, the encrypted message, it might be trivial for a human to look at it and tell what the original message was. Let's say, for example, if your message was A, B, C, D, and the network produces the ciphertext A, C, B, D. So according to the network, 50% of the characters are different, meaning that it has almost successfully encrypted the message. But to a human looking at ACBD, you can probably guess that what it means was ABCD, with the semantic understanding of language that we have. So that is a thing that we need to look at. A few problems that we need to fix, address, etc. The encoding of text. First of all, encoding, or as people in the business call it, word embeddings. Word embeddings work for only things that are present in the dictionary. Currently, there are two algorithms, two networks that I'm looking at, which are Word2Vec, which is mentioned here, and GloVe encodings, embeddings. What GloVe does is also similar to Word2Vec, but it's slightly better. The issue with both of these algorithms is that they don't actually work with any data. They don't work with arbitrary data, which means that you can't just send binary data, as is very often required in computation. You can't just send binary data to the network and say ki bhai you should embed this into an encoding. So because the network requires a vector of numbers, it doesn't work with characters, it works with numbers. So how do you represent a character as a number, not just its ASCII value, but because that ASCII value thing is again very simplistic, it doesn't work. So how do you represent a number semantically? That is the point of Word2Vec and GloVe. But we don't necessarily need to represent it semantically. We need to represent it as part of some data. So that is something that we need to look at. This thing about adversarial agents being too weak that I talked about. Now there is a problem in this whole system, that Eve here in this whole system, Eve here is too weak. The job of, if you look at just Eve, the job of Eve is to take in this ciphertext. The only input it has is this ciphertext, and it is supposed to produce some plain text PE. It doesn't know how to do this. No neural network will be able to do this without any training. So how does Eve even do this? How does Eve even begin to look at this problem? So the eavesdropper's job in this system is very hard. That is why it always sort of is lagging behind, and it's always a weak system that creates a false sense of security again, and Alice is able to easily send across their messages. So this is a problem that has to be solved. There are two ways that I've read about that can solve this problem. I have a third proposal that I would like to experiment on. One proposal that was given in the M. Coutinho paper in Sensors, the 18th version, was that there are two plain texts instead of a random instead of a single plain text. There are two types of plain text. Let's say there's P1 and P2, okay, and there are only these two plain texts. So what you do is you randomly choose a plain text P, let's say P1, okay, and you give that to Alice. Now Alice does its thing normally and Bob does its thing normally. The key is distributed normally. The only difference is that that plain text P1 also goes to Eve, sorry. It goes to Eve because uh, this makes its job much easier. So Eve's job now is to look at the plaintext P and the ciphertext C and to tell us whether or not this ciphertext came from this plaintext. That is Eve's job. Now, can it do this? Yes, it can. It is a much easier problem to solve for Eve now, that it has the original version and it has the encrypted version. It has to, the only thing now it has to do is say whether or not the encrypted version came from the original version. If it says no, then its loss is high. If it says yes, then its loss is low. So that is how the training of Eve can work. This has shown to produce better results than this system described here. Okay, and we will also look at that system. My proposal to this is again trying to make this better by introducing more variables to the system. Suppose we take the problem with this two variable thing is that uh, 50, let's say the distribution of randomness is random, okay. It's a 50-50 distribution between P1 and P2. 50% of the time P1 is input and 50% of the time P2 is the input. So if Eve produces a random result, its probability of being right is the probability of it producing 1, which is 50%, into the probability of it of the plaintext being P1, which is again 50%. So Eve can only ever be right 25% of the time, and that creates a very that's a skewed distribution towards being wrong 75% of the time and being right 50% of the time. So that means Eve is still very weak. Now what I propose is that we introduce a distribution. We introduce a sort of a database of texts, and we encrypt them. And we encrypt them with this system, with a trained Alice, right? We take a standard algorithm and we model Alice after a. This is one of the proposals again. I mean, I'm not trying to. Okay, I'll just put these proposals separately. Okay, this video will become too long. I'll just put these as separate things, right? Um, anyway, so this is one problem. Again, synchronization I talked about. This is another problem, that there is data loss. We need to account for that. Then again, the key exchange algorithm is again vulnerable to attack by a human, which means that if you know the key, you will be able to train the network, which is a problem. So we need to take care of that as well. That for that we can use a typical key exchange algorithm like ECDH or something like that, or we can even go for an asymmetric encryption scheme. So yeah, that is the work until now. These are some of the references that we've been using. This is this paper by Cantor. This is the one which tells us that networks can be synchronized. This is the main paper that we are basing all of this on, the Abadi paper. This is the Coutinho paper that gives one way of improving this communication, and there's this another paper that I've sort of consulted. It's about multi-agent communication. It's not very relevant, but it is sort of relevant.